Okay, good morning, Pierre Chatelain. Okay, we are there for your defense, your PhD defense. The jury shoot me as president, and then I will first introduce the jury members. The jury is composed of Purang Abolma Isumi. I was the first reviewer. I was the second reviewer, but as Ross could not be there for the jury, I also have the charge of be president of this jury. Then there is one examiner, Céline Foire, who is assistant professor at the University of Joseph Fourier in Grenoble. Purang Abolma Isumi is a professor at the University of British Columbia in Canada. And your supervisor was Alexandre Coupa, who is a researcher at Inria Rennes, and Professor Nasir Nawab, who is a professor at the University of Munich, Technical University of Munich. He was co-supervisor of your PhD. While you will present your work titled Quality Drive and Control of Robotized Ultrasound Probes, and you have now 45 minutes for presenting your work. Afterwards, we will ask you for questions. Okay, it's up to you now.
Thank you. So thank you for attending my PhD thesis. I'm going to present some contributions of my thesis on the topic of quality-driven control of a robotized ultrasound probe. So this thesis was conducted in the context of an international co-title under the joint supervision of Alexandre Coupa from INRIA and Nasir Nawab from the Technical University of Munich. Ultrasound imaging is used in a wide range of medical applications. First of all, for diagnosis, where we can mention, for instance, obstetrics, cardiology, vascular screening, and also emergency for the assessment of trauma. One advantage of ultrasound compared to other imaging modalities is that it can provide images in real time at a very high frame rate, which is very important for imaging moving structures, such as, for example, the Earth. Ultrasound is also gaining interest for interventional imaging, for monitoring percutaneous procedures such as biopsies or drug delivery. So here again, the real-time capability of ultrasound is a clear advantage in order to precisely monitor the insertion of the surgical instrument. In addition to visualization, ultrasound is also used for treatment by sending high-intensity focused waves on a localized target. One of the first motivations for the development of robotic ultrasound was teleechography, in order to allow an expert clinician to perform an exam on a patient located in a remote site. So in this context, the robot can provide some functionalities to assist the clinician in the manipulation of the probe, for instance, by providing a force control, an automatic force control of the ultrasound probe during the examination. More recently, ultrasound robotic assistants have also been considered for interventional imaging in order to assist either in the insertion of the instrument or in the manipulation of the ultrasound probe in order to maintain the visibility of the surgical instrument. Some research teams have also proposed robotic assistance for IFU in order to compensate for tissue motion and so to increase the precision of the treatment. In this context, the general objective of my thesis was to design an intelligent robotic system that is able to assist the clinician by providing some degree of automation in the manipulation of the ultrasound probe. More specifically, I have focused on control strategies for optimizing the quality of ultrasound acquisitions, so for instance, by avoiding imaging artifacts such as shadowing. So in the first part of my presentation, I will introduce some existing approaches on the control of an ultrasound probe or the control of an instrument under ultrasound guidance. On this topic, I will present a first contribution of my thesis on the topic of flexible needle steering under 3D ultrasound guidance in a closed loop. Then in the second part of my presentation, I will address the main topic of my thesis, which relates to the control of an ultrasound probe in order to optimize the quality of the acquisitions. So the problem of controlling a robot from visual data can be modeled as a closed-loop control scheme where a visual error E is computed as the difference between a current feature S extracted from the image and a desired value of this feature vector S star that we want to reach. The relation between the variation of the visual feature and the velocity of the robot can be modeled by an interaction matrix. And if we have a good approximation of this interaction matrix, or a numerical estimate of it, then we can design a visual servoing control law that will minimize the visual error. In the case of ultrasound-based visual servoing, the visual sensor corresponds to the ultrasound probe, and the visual data are extracted from the ultrasound images. So the goal of ultrasound-based visual servoing is to control the motion of a robot using information extracted from the ultrasound images. However, the use of the ultrasound modality to control a robot brings some challenges. First of all, we need to extract relevant information from the images. This can involve, for example, a segmentation or tracking of an object of interest, or the extraction of different features that will be of use for the design of the control law. In order to leverage the real-time capability of ultrasound imaging, these algorithms also need to be fast enough to process the images in real time. In addition, we need a model of the interaction between the variation of the image and the motion of the probe or the motion of an instrument. In particular, for the case of 2D ultrasound probes, the variation of the image with respect to out-of-plane motions is quite difficult to predict. So this poses some problems of interaction modeling. Finally, the quality of ultrasound images is relatively low compared to other imaging modalities, and it is also non-uniform within the images and non-constant. So we can distinguish two types of configurations for ultrasound-based visual servoing. In the I-in-N configuration, the robot directly controls the motion of the ultrasound probe, while in the I-to-N configuration, the robot controls the motion of an instrument which is observed by the ultrasound probe. So we'll first review some methods for the I-in-N configuration. Here, for instance, we can extract geometric visual features from the images, such as points or contours. For instance, Abolma Issoumi and colleagues use the tracking of the center of the carotid artery as a reference point to perform motion compensation during teleoperation. So in this context, the control of the robot is shared between the clinician and the automatic controller, which aims at centering the carotid artery in the image. We can also consider other sorts of geometric visual features, such as the contours of objects. For instance, Mebarki and colleagues use moments extracted from the contours in order to perform a positioning task, so to bring the section of the object into a specific configuration. In this case, we also need a 3D model or a local 3D model of the shape in order to predict the variation of the contour with respect to out-of-plane motions. However, one limitation of geometric approaches is that the tracking or segmentation algorithm needs to be perfectly robust for the control law to converge. Because if we lose the target or the contour, if we missegment the contour, then this can lead to undesired behavior of the control law. For this reason, intensity-based approaches have been proposed, where the intensities of the ultrasound image are directly used to define the visual feature. For instance, Nakadate and colleagues use the sum of square distance between the current image and desired view in order to perform motion compensation along 1 degree of freedom in the out-of-plane direction. More recently, Nadeau and Krupa proposed a direct visual servoing approach, where the visual vector S is directly defined as the vector of intensities in a fixed region of interest. Then the authors use the pixel-wise difference between the current view and the desired view in order to perform a motion compensation task with 6 degrees of freedom. If we now consider the I-to-N configuration, the robot can be used, for instance, to adjust the insertion path of a rigid needle in order to align its trajectory with the target that we want to reach. But if we have a flexible needle, then we can control the insertion path even more precisely in order to reach a specific target while avoiding sensitive structures such as vessels or other organs. However, most of the approaches that are existing for a flexible needle insertion consist in a path planning approach where the insertion trajectory is planned in advance and then executed. However, in order to obtain a very high precision and to avoid the obstacles in real time, then we also need to visualize the needle, so to track it in the images in real time, and to perform a closed-loop control thanks to this tracking. In this context, I will propose the first contribution of my thesis, which consists in a needle steering approach for flexible needles under 3D ultrasound guidance. So the goal is to drive the flexible needle towards a specific target using only the information provided by 3D ultrasound. To this end, we first need a method to track the needle in the ultrasound images. There we can use, for instance, a polynomial curve in space to represent the shape of the needle. So the shape will be defined by a set of control points which define the polynomial curve. Then, in order to infer the most likely shape from the ultrasound data, we can use a Bayesian tracking approach where the state of the system, xt, is defined as a set of control points defining the needle. And in order to infer the most likely shape, we need a kinematic model or a mechanical model in order to predict the evolution of this shape in time, and an appearance model in order to measure the correspondence between the estimated shape and the observation. So to infer the most likely state from the observations, we can refer to a particle filtering approach where the probabilistic distribution of the state is modeled by a set of weighted particles. So the weight of each particle will correspond to the likelihood of the state given the current observation. In this simple 2D example, the different particles are represented as blue points and their size is proportional to their weight. And using the kinematic model and appearance model, we can successively update the state estimate of the different particles and re-estimate their weights, so their likelihood. Then the current estimate of the state is defined as the weighted sum of all particles, which corresponds to the expectation of the state given the observation. In the case of needle tracking, each particle will correspond to a possible needle shape, and the weight will measure the correspondence between this shape and the current ultrasound image. As the needle usually appears as a bright line in the echo because of high intensity reflections on the needle, we propose to define the weight as proportional to the mean intensity along the shaft of the needle. And in order to precisely detect the tip of the needle, we add a secondary term which is proportional to the intensity at the needle tip. This is to ensure that the curve will stop precisely on the tip of the needle. Now that we have a model for the appearance of the needle, we need a kinematic model. Here we can use the assumption that the velocity, the insertion velocity of the needle, propagates rigidly along the shaft of the needle. That is, there is no compression of the needle along its axis. Using this assumption, we can update the different control points using the tangent to the curve at each control point. And in order to model the uncertainty and the motion model, we add a noise term to the update equations. And the effect of this noise term will be to spread the distribution of the different particles to explore the state space. So now that we have a method for tracking the needle, we'll have a look at how we can steer it towards the desired direction. Here we can refer to the duty cycling strategy for bevel tip needle, which allows to precisely control the motion of the needle tip. So if we consider a bevel tip needle, the asymmetric forces that are exerted at its tip will induce a circular insertion trajectory while the needle is pushed forward. On the other hand, if we rotate the needle around its axis while it is inserted, then the tip will follow a helical path, which can be approximated to a straight path if the rotation is fast enough. And by playing on the ratio between these two types of motion, we can obtain an effective curvature which will be lower or equal to the natural curvature of the needle, and we can therefore steer the needle in the desired direction with the desired curvature. Now, in order to drive the needle towards the target, we propose to use the approach proposed by Krupa, which is a visual serving approach, where the visual feature is defined as the distance between the target and the direction defined by the tangent to the needle at its tip. So this visual feature can be extracted directly from the ultrasound images using the tracking approach that we have proposed. And the goal will be to bring this visual feature to 0 so that the needle can reach the target in a straight path. To this end, we use a visual serving approach to control the rotational velocity of the needle tip from the visual feature. And using this control under a constant insertion velocity, we can go back to the duty cycling approach and compute the effective curvature and the orientation of the bevel of the needle that we want to obtain in order to have the desired control velocities of the needle tip. So using this approach, we can precisely drive the needle towards a specific target using only information extracted from the ultrasound images. So in this video, we can first see the tracking of the needle in a simple insertion experiment without needle steering, where we can see the detected needle in red, and the blue points correspond to the position of the needle tip for all particles. So it's the point cloud of particles. And then we can observe the natural curvature of the needle. In this second sequence, we use our closed loop control in order to drive the needle towards the green target. So here we can observe the robot on the bottom right of the video performing rotations in order to correct the insertion trajectory of the needle. And as we get closer to the target, the needle tip gets aligned with it, and the robot performs more and more rotations in order to keep a straight trajectory to reach the needle. At the end of the insertion, we reach the needle with an accuracy of 1 millimeter, which is about the same size as the resolution of the ultrasound volume. So to conclude this first part, we have seen that it is possible to use visual servoing to control the motion of an ultrasound probe in order to perform a positioning task or motion compensation task, or to control the motion of an instrument under ultrasound guidance. And on this topic, I have proposed a first contribution, which consists in a needle steering approach under 3D ultrasound guidance in closed loop, where we use particle filtering to track the needle in the ultrasound volume. One limitation of most ultrasound-based visual servoing approaches is that the algorithm assume a good image quality, and they rely on a good image quality in order to perform well. However, the quality of the ultrasound signal can be non-uniform in the images and also non-constant. For instance, if we consider geometric approaches, a shadow in the image can lead to a missegmentation of the object of interest, and so to a misalignment of the ultrasound probe using a classical visual servoing approach. So the ultrasound probe will not reach the desired configuration. Similarly, for intensity-based approaches, if we have a shadow covering a part of the region of interest, then we will have a mismatch in the image difference between the current view and the desired view in terms of intensity of pixels. And this mismatch can lead also to a divergence of the control loop. For this reason, I have focused in my thesis on control strategies to optimize the quality of ultrasound images. So I'll now move on to the main topic of this presentation, starting with methods for estimating the quality of the ultrasound signal. In order to understand the problem of ultrasound image quality, it is interesting to have a look at the formation process of ultrasound images. So ultrasonography consists in sending an ultrasound wave into the body and listening to the echoes that are produced by tissue interfaces. So at each interface between tissues of different densities, part of the ultrasound wave will be transmitted further deeper in the body, and part of the ultrasound wave is reflected back to the transducer, which produces an echo. By listening to this echo, we can register a radio frequency signal, which corresponds to the amplitude, to the intensity of the echoes. And this radio frequency signal is then deconvolved, envelope detected, in order to obtain the amplitude of the echo response. This process is repeated for each scan line in the image in order to produce a 2D representation of ultrasound response. However, if we have a strong interface on the path of the ultrasound wave, then the wave can be fully reflected by this interface, which will produce a shadow deeper in the image. So a part of the image will not be visible because the full wave is reflected at the strong interface. So for this reason, the quality of the ultrasound signal can be non-uniform within the images. We can see here on the left a dropout artifact which results from a bad contact between the ultrasound probe and the skin of the patient. And on the right, a local shadow which is due to a local difference in tissue densities, which is higher than normal. And more generally, the amplitude of the ultrasound wave also decreases with the distance traveled by the wave. In order to estimate the quality of ultrasound images, Karamalis and colleagues proposed the concept of confidence maps, where each pixel in the image is assigned a confidence value between 0 and 1, which measures the quality of the ultrasound signal at this location. So this method gives a way to distinguish between low confidence regions and high confidence regions in the image, and so to detect shadows. So the confidence map is a pixel-wise measure of signal quality, which is based on a model of ultrasound propagation in soft tissues. If we go a little bit more into the details of this method, it relies on the random walks formulation, where the confidence at each pixel is defined as the probability that a random walks reaches one of the transducer elements under certain constraints, which model the propagation constraints of sound in the soft tissues. So the image is represented by a weighted graph, where each node corresponds to a pixel. So each column in the graph will correspond to a scan line. And the edges between the nodes are weighted according to the propagation model of ultrasound. So if we consider, for instance, the vertical weights, these weights model the propagation of the sound along the scan lines, and they rely on the gradient of the image. Lateral weights are defined in a similar way. However, they incorporate an additional term that ensures that the ultrasound wave does not disperse laterally. So it limits the lateral dispersion of the ultrasound wave. This is to model the principal direction of propagation of the ultrasound wave along the different scan lines. Then these two terms also depend on an exponential attenuation of the ultrasound image with the distance to the transducer. In order to solve the system, we need also two boundary conditions, which are defined as a perfect confidence next to the transducer and a confidence of 0 at the maximal depth. And then we want to estimate a value for all pixels in between, so to assign a value between 0 and 1. Using the random walks model that was proposed by Grady, we can define the confidence as a solution to a sparse linear system which depends on the Laplacian matrix of the graph and the two boundary conditions. And this system can be solved using a standard sparse linear solver. And we thus obtain this representation of the confidence map. So this is a good representation of ultrasound signal quality. However, it also has some limitations. First of all, it is quite computationally expensive, so that we need to downsample the images in order to obtain a real-time processing of the confidence map. In addition, the results are not smooth with respect to time, which can be a problem to use this signal for a control law, because we don't have a good stability in time of the ultrasound signal quality estimates. For this reason, I've considered another method, an alternative method to estimate the quality of the ultrasound signal, which relies on an integration of the envelope detected radiofrequency signal along each scan line. So here we build up an additive acoustic loss by summing up the RF signal amplitude. And in order to obtain values between 0 and 1, we normalize this additive acoustic loss by the sum over the entire scan line. Then we obtain a new representation of the confidence as shown on the right. So this new model is less regular in space. However, it has other advantages. First of all, it is extremely fast to compute. It can be estimated in linear time with respect to the size of the images, which is much faster than for the random walks approach. And it is also smoother with respect to time if we compare it to the random walks approach. So in this graph, we use two different measures of temporal regularity to compare the two approaches, and we obtain significant results, which shows that the new approach is more regular with respect to the time than the random walks approach. So now that we have a method for estimating the quality of the ultrasound signal, I will propose a framework for optimizing the quality of ultrasound images using a control law. So if we go back to ultrasound-based control, we usually have the association of two tasks. So first, a force control task, which consists in maintaining a constant contact force with the body, and then a positioning task, which can be either an automatic motion compensation task or directly the teleoperation by the clinician. Then we propose to define an additional task where we will use the confidence map as a new visual modality to control the orientation of the ultrasound probe in order to optimize the quality of the images during the positioning task. To this end, we need to have a model of the interaction between the variation of the confidence map and the motion of the probe. There we can first have a look at the relation between the contact force, or the vertical translation of the ultrasound probe, and the quality of the images. We already know from experience that it is necessary to apply a sufficient force on the body in order to obtain a high quality image. Using the confidence map, we can now verify this with our measure of ultrasound signal quality. And interestingly, we observe that the mean quality of the signal increases first while the contact is made, but then above a threshold, the mean quality will be constant, so will not be dependent of the contact force. This means that above a certain threshold on the contact force, it is not necessary to apply more pressure on the body because it will not improve the quality of the images. So of course, the specific threshold value will vary from a patient to another, but we already know that there is always this plateau from a certain point. So the main motion that will impact the quality of ultrasound images is the orientation of the probe. And for the case of a 2D convex ultrasound probe, we can make the interesting observation that a rotation around the imaging center of the ultrasound probe corresponds exactly to a rotation of the confidence map. This observation motivates the definition of a visual feature as the angular coordinate of the confidence barycenter to represent the optimal acoustic direction in the image. And then we have shown that under a pure in-plane rotation of the ultrasound probe, the time derivative of this feature is equal to the in-plane rotation velocity of the ultrasound probe. So this is an interesting feature to use in a control. If we look at different images for different orientations of the ultrasound probe, we can see the evolution of this visual feature, which always indicates the direction in which the optimal acoustic position could be reached. So the behavior that we expect from the system by bringing this visual feature to 0 is that in the presence of homogeneous tissues, the probe will be maintained at the normal to the surface in order to have a balanced image quality, while in the presence of a shadowing structure, the probe will be reoriented in order to avoid this shadow. Then, in order to control the robot based on this feature, we need to define a model of the interaction matrix between the velocity screw of the probe and the variation of the visual feature. We have already seen that the omega z term of this interaction matrix is equal to 1. And we will make the assumption that all the other terms are 0, which amounts to considering other motions of the ultrasound probe as perturbations to the system. And we will see through the experiment that this assumption, while it is a strong assumption, it is valid and it does not yield any instability in the system. Then, if we want to do 3D imaging with, for example, a wobbler probe, as here, then we can generalize the approach that has been proposed by defining similarly a second angular feature as the previous one, which will provide the optimal acoustic direction in the other direction. Then we also want to bring these two visual angles to 0 in order, which corresponds to the central line of the volume, in order to have the maximal confidence in the center of the volume and to balance the confidence around the center of the volume. And for these two visual features, we can obtain, using the same assumption as previously, this interaction matrix, this approximation of the interaction matrix. And using a classical visual servoing control law, we obtain a global quality optimization. So in this video, we can see the system converging to the desired configuration, so normal to the surface of the phantom. And at convergence, we reach an accuracy which is below than 1 degree. And this is lower than the angular accuracy of the ultrasound volume. Then if we insert a band of paper between the probe and the phantom in order to generate locally a shadow, then the system reorientates itself in order to avoid this shadow. So we can test this on different orientations. The system always avoids the shadow by reorienting the ultrasound probe. So we have considered an application of this method to teleechography in order to optimize the quality of the ultrasound images while the probe is being teleoperated by the clinician. So in this case, the clinician controls the translations of the ultrasound probe on the surface, and the goal of confidence control is to optimize the orientation of the probe during teleoperation in order to maintain a high quality of image, to facilitate the manipulation of the probe by the clinician. So in this video, the vertical translation is again controlled by the force controller. The orientation is controlled by the confidence controller, and the translation is teleoperated by a user. And we observe that the system allows to maintain an optimal orientation for the ultrasound probe, even when we want to image heavily shadowed areas, such as between the ribs. We can see a large rotation of the probe, which is fully automatic. So the approach that I have proposed optimizes globally the image quality without considering the specific content of the ultrasound image, any specific anatomical structure. Now, for some applications, it would be desirable to optimize the quality for a specific target that we want to track in the images. And this can be seen as the problem of optimizing the acoustic window for the target, where the acoustic window is defined as the position and orientation of the ultrasound probe with respect to the target. For instance, we can see here on the left a non-optimal acoustic window where there is a shadowing structure on the path between the ultrasound transducer and the target. And on the right, an optimal acoustic window where the ultrasound can reach the target and propagate back to the transducer without hitting any major interface. So we now define a new scheme for controlling the probe where we have an automatic positioning task which aims at centering the target in the ultrasound images, and a confidence control task which aims at optimizing the quality for this target without disturbing the target positioning task. If we first have a look at the target positioning task, we can define this task as centering the target in the ultrasound image horizontally, so to have the target aligned with the middle of the image. And this can be done, for instance, by defining the visual feature as a geometric feature, which is the distance between the center of the image and the center of the target. And we obtain, using this visual feature, a classical interaction matrix for the control of the target. Then, in order to optimize the confidence for the specific target, we need to modify the confidence feature to take into account also the position of the target in the image. To this end, we can define the new feature SC as the angle between the target and the optimal acoustic direction. And using this new feature, we can have a new approximation of the interaction matrix that links the variation of this feature to the motion of the ultrasound probe, where this new interaction matrix takes also into account the position of the target in the image. Finally, in order to ensure that the confidence control task does not disturb the other tasks, we need to define a priority between the different tasks. So the first control will be the task of higher priority, the first task. Here we simply define the first control task using an elastic model of tissue deformation. And so we have a control along 1 degree of freedom. Then the positioning task is a second task, and which aims at centering the target in the image. And the task of lower priority consists in the confidence control task, which will act on the orientation of the ultrasound probe around the target. If we look at the interaction matrices of these 3 tasks, we notice a coupling between the third task and the 2 first, so that we need to project the velocity of the third task on the kernel of the first 2 tasks in order to ensure that the third task will not disturb the first one. In addition, we take into account the contribution of the first 2 tasks to the third one in order to also have an exponential decrease of the error for the third task. And using these modified task velocities, we define the global velocity as the sum of these modified tasks. So in this video, we can see the system converging to the desired configuration with the target centered in the image and the confidence optimized for this target. In this experiment, the region abstract thanks to a template matching algorithm. And at convergence, we reach excellent accuracies. In particular, for the position task, we have an accuracy which is lower than 0.2 millimeters, while the size of a pixel is approximately 0.5 millimeters. Similarly, for the confidence control, we always have precision on the visual feature which is lower than 1 degree, while the angular resolution of the ultrasound probe is of the order of 1.5 degrees. Now, if we move the phantom in order to disturb the system, we can see the robot tracking, so following the target while maintaining an optimal orientation for the ultrasound probe. Similarly, if we insert a band of paper in order to generate a shadow, then the system reorientates itself in order to optimize the quality, to maintain a high quality for the target, while maintaining the target centered in the image. in these different graphs, we can see on the top the convergence of the three control features towards their desired value. In particular, we observe a good decoupling between the confidence and target positioning task, and as can be seen on the target positioning graph, where the visual error decreases in an exponential manner to 0. On the bottom, we can see the evolution of these three features during perturbations of the system, which are highlighted in gray. And we observe that despite the increase of these visual errors during the perturbations, the visual features always converge back to 0 during the rest motion, which are indicated by the white areas. Now, in order to assess the impact of confidence control on the quality of the tracking, we need to define a measure in order to estimate the quality of the tracking and to assess whether the tracking is successful or not. To this end, we propose to use a normalized correlation between the current region of interest and the initial template. So this is for a template matching algorithm to follow the target. And if we compare the evolution of the normalized correlation in experiments without confidence control and with confidence control, we observe that the confidence control significantly improves target tracking. In particular, it allows to maintain quasi-constant the normalized correlation during the procedure, even during perturbations of the system, which are indicated by the gray areas. So in this new video, we can see an experiment of tracking without confidence control. And here, because we do not ensure the visibility, the confidence of the target, the tracking can fail. So here, if we move the phantom, the target can go into a shadowed area, and so the target will not be precisely aligned with the desired target. Finally, I would like to present some experiments that we perform on a human volunteer in order to validate our approach in a more realistic scenario, so closer to a clinical setup. So in this experiment, we ask the patient to lie down below the ultrasound probe, and the KUKA robot is controlled thanks to a shared control between the teleoperator and the global confidence-driven control that I have proposed. So here we can see that the system allows to maintain at all times an optimal orientation for the ultrasound probe, which yields a high quality of image. So here we use the 3D ultrasound probe to image the patient. The only difference with the experiments that we performed on Phantom is that in this case we use the internal force controller of the KUKA robot in order to ensure the safety of the procedure. Then we tried different orientations for the ultrasound probe. So here we are imaging the patient from the side, and the system is still able to find an optimal orientation to obtain high quality images. Then in order to further test the reaction of the system, we ask the patient to breathe deeply, and despite the wide amplitude of the respiratory motion, which is of the order of 4 centimeters in the elevational direction, the system is still able to compensate both in terms of contact force and in terms of image quality. So to conclude my presentation, I've proposed the first contribution, which consists in a method for steering a flexible needle under 3D ultrasound guidance, where the needle is tracked in the ultrasound images using a particle filtering approach and controlled in closed loop using the result of this tracking approach. Then I've proposed a control framework for optimizing the quality of ultrasound images. So first a global approach where the image quality is optimized globally, and then a target-specific approach where we optimize the acoustic window for a specific target which is tracked in the images. We have performed a validation of these approaches on 2 different robotic platforms. So first at Inria and also at the Technische University of Munich with different robots and different systems. And we performed the first validation on a human volunteer, which constitutes a first step towards the clinical validation of the approach. In the future, I think that we could go in the next few years towards the clinical validation of quality optimized teleechography. Indeed, some commercial products already exist for teleechography, which propose control of the contact force with the body. So here our approach will be another functionalities that can be added to teleechography, and which simply optimizes the orientation of the ultrasound probe. Then we could also imagine other applications of quality optimization, for instance, to acquire a high quality image of a larger volume of interest, so for example a full organ that we want to image. Here we could use, for instance, the preoperative images in order to plan a trajectory of acquisition that will optimize the quality of the reconstructed volume. On a more technical level, I think there is still some room for improvement also on the quality estimation itself and on the modeling of the interaction between the confidence map and the motion of the ultrasound probe. On the longer term, it would be interesting to consider a confidence optimization approach for intraoperative imaging in order to optimize the quality for both targets that we want to reach and for the surgical instrument. So here we will have to take into account, in addition, the artifacts that are produced by the insertion of the instrument itself. Finally, for a full clinical integration of quality optimization, I think we should go towards a system where we propose a control strategy to optimize directly the outcome of the procedure globally. For example, to optimize the precision of measurements that we want to make from the ultrasound acquisition. Finally, there is a list of my publications, and I thank you for your attention.